Welcome to The Explainer. Today we're diving into something kind of weird, a really subtle but fascinating challenge facing modern AI.
And that right there, that's not science fiction. That's the bizarre, kind of unsettling world of adversarial noise. It's like a ghost in the machine, right? It fools our most powerful AI into seeing things that just aren't there.
So let's really get into it. What is this digital camouflage? And maybe more importantly, how on earth does it work? Okay, so what are we talking about here? Put simply, it's this: carefully designed static. Think of it like a digital whisper. It's almost always completely invisible to you and me, but it's just enough to completely trick an AI into making a decision that is, well, confidently and totally wrong.
Now, you got to understand, this isn't just some random glitch in the system. No, this noise is mathematically engineered. It's designed specifically to exploit the very logic an AI uses to learn in the first place. And here's the part that's really alarming. It's transferable. That means an attack designed to fool, say, Google's AI could very well work on a totally different model built by someone else. That's a huge problem.
And look, this is not just some theoretical thing stuck in a university lab. These kinds of attacks have serious, real-world consequences.
Because the threat isn't just about tricking an AI with a photo. Oh no, it completely changes based on the medium. We're talking about ultrasonic commands hidden in audio that you can't hear, tiny flickers in a video you'd never notice, or even invisible characters slipped into text to completely change its meaning. And each one of these is its own unique, really difficult puzzle to solve. And this is where it gets scary, because this vulnerability strikes right at the heart of systems we're beginning to trust with our actual lives. Just imagine it: a self-driving car that's tricked into blowing right past a stop sign, or a medical AI that's manipulated to miss a tumor on an MRI. The stakes literally could not be higher.
Okay, so if this stuff is basically invisible, how in the world do you fight back against something you can't even see?
Well, the first line of defense is this multi-step detection process. You can think of it like a digital CSI unit. First, they do statistical analysis, just looking for any weird patterns in the data. Then, you might have a second AI, a guard dog AI, if you will, trained specifically to spot these fakes. They can even do things like add more random noise just to see if the AI's prediction suddenly gets all shaky. It's all about finding those clues before any real damage is done. But, and this is a big but, there's a catch. Our detection methods are basically locked in a constant race with the attacks. Yeah, they're pretty good at catching the older, simpler stuff, like the FGSM attacks. But when you get to the more sophisticated, more subtle attacks, things like the CNW method, that's where our defenses really start to struggle to keep up.
So since just detecting these things isn't going to cut it, the focus is shifting. It's moving towards building a kind of digital shield, creating systems that are just tougher and more robust right from the get-go.
And the main strategy for this is something called adversarial training. It's a great name for it, and you can really think of it like a vaccine for the AI. You're intentionally exposing the model to these fake attacks in a safe, controlled training environment. You teach it to see them, recognize them, and classify them correctly anyway. The goal is to build up a kind of digital immunity.
And just like the attacks are different for different media, the defenses have to be too. Each type of data needs its own specialized shield. For audio, that might mean using filters to cut out those ultrasonic frequencies. For video, you apply smoothing to make sure one frame isn't wildly different from the next. It's all about neutralizing these attacks before they can ever get to the AI's core logic.
But this leads to one of the biggest headaches in the whole field. It's called the accuracy-robustness trade-off. And what that means is, the more you make an AI into a fortress, really tough against attacks, the more it can actually hurt its performance on normal, clean data. It becomes a little less accurate in its day-to-day job. And for researchers, that is a constant, frustrating balancing act.
And all of this really brings us to the bigger picture here. This isn't a problem that you can just solve once and walk away from. Not at all. It's a constant, evolving battle. It's an arms race between the attackers and the defenders. I mean, just look at how fast this whole thing has moved. Back in 2014, this was a weird, niche discovery that only a few academics were talking about. Just a few years later, boom, the attacks jumped from being purely digital to affecting physical objects in the real world. And now
Now we're in a full-blown arms race, with new attack and defense techniques popping up all the time.
But the defenses are nowhere near perfect, which brings us to a pretty sobering number, 23%. For some of these detection systems, that's the average false positive rate. Let that sink in. It means our digital shields are so cautious, they're incorrectly flagging almost 1 out of every 4 completely normal, safe inputs as a potential attack. That's not just an inconvenience, that's a massive usability problem.
And what's maybe even more concerning is what gets through. 85%. Now you hear that, 85% detection for brand new novel attacks. And you might think, hey, that sounds pretty good. But it's the other side of that number that keeps security experts up at night. It means 15% of the newest, most sophisticated attacks are slipping through completely undetected. And in the world of security, a 15% failure rate isn't a gap, it's a wide open door. It's a critical failure. So, where do we go from here? The ultimate goal has to be a shift in our thinking. We have to stop just patching on defenses after the fact. The real future has to be in security by design. That means building AI models that are fundamentally secure and robust from the very first line of code.
And this all leaves us with a huge, critical question that we absolutely have to solve. As AI becomes the eyes and ears for our cars, for our hospitals, for our security systems, how do we make sure we can actually trust what it's seeing? Answering that, well, that's not just some technical puzzle. It's fundamental to the entire AI-powered future we're building.